Yesterday we have seen introduction to MIMO process. We didn't finish yesterday. Today, let us finish the remaining topics in MIMO process. MIMO process. If a process has more than one input and more than one output, then the process is called MIMO process. But each loop in the MIMO process can be seen as independent SISO process, single input, single output process. That way only we can tune each loop. That is different story. But the problem with the MIMO process that we have seen yesterday is, suppose we are having two process variables, P1 and P2, P1 and P2, that is Y1 and Y2. In that case, two inputs are there, M1 and M2. Which manipulated variable has to be used to control Y1? Which manipulated variable has to control Y2? That we have to decide, because the process M1 can also be used to control Y1 as well as Y2, because if you change M1, both Y1 and Y2 are changes. That is called interaction. If one manipulated variable is adjusted, then both outputs are changing. That is called interaction of M1 with Y2. But we want to change M1 to change Y1, but Y2 also changing. That is called interaction. Similarly, if we change M2, then Y1 also changing. That is called interaction. Because of interaction, we should select appropriate manipulated variable that gives minimum interaction. First thing is, it should give minimum interaction with the other loops. At the same time, it should have very effective control over the variable for which it is manipulated. Suppose M1 has very good control over Y1, but it has minimum interaction with Y2, means M1 can be selected as manipulated variable for Y1. Similarly, M2 has very good control over Y2. Very good control means it has small changes in M2 has very good changes, large changes in Y2. While compare with other manipulated variables, then M2 should be used with used to manipulate Y2. That is called very good control over Y2. So M2 have very good control. M2 has very good control over Y2. Therefore, M2 is used here. Suppose M2 has very good control over Y1 and M1 has very good control over Y2, then we should configure this way. We should configure this way. M1 should be regulated, manipulated to control Y2. Similarly, M2 should be manipulated to regulate Y1. So all depends upon the impact of M1 on M2. Impact of M2 on Y1 depends upon that, and minimum interaction. Based on that, yesterday we have discussed that for a four process variables, FF, pressure, temperature, level, all the four variables has to be manipulated. For that, yesterday we have seen that feed flow rate, liquid flow rate, and steam mass flow rate, and vapor flow rate are used to control these four variables. But if you put the permutation combinations, there are 24 possible combinations. That way we can control all these four variables. But which among the which one among the 24 is best, that we have to find. Yesterday we have seen that by using qualitative analysis. Yesterday we did by using that qualitative analysis. By that we selected FF to control feed flow rate, FV vapor flow rate to control pressure, and steam mass flow rate to control temperature, and FL, that is liquid outflow rate to control H. In that way, we selected these four variables to control this flash drum. This flash drum. Where is that flash drum? So in this flash drum, pressure has to be controlled, temperature has to be controlled, out of how many variables? 2n plus 7, 2n plus 7 variables. Um, uh, we have to control pressure, temperature, feed flow rate, and the level. Four variables has to be controlled. For that, what are the manipulated variable we have taken? Feed flow rate to control the feed flow rate. The vapor flow rate, this is another manipulated variable. Manipulated variable to control pressure, and steam mass flow rate to control the temperature. This liquid flow rate to control H. That way we have seen yesterday. Why only four variables are controlled for this distillation column? That also we have seen, because out of 2n plus 7 variables, the remaining are constants and defined by external, maybe random variable or constants. Those out of 4n plus 14, out of 4n plus 14 variables, 2n plus 7 are constant and externally defined. And we have how many equations? 2n plus 3 equations. Therefore, degrees of freedom equal to degrees of freedom F equal to 2n plus 7 variables, 2n plus 7 variables, unspecified variables, minus the number of equations that relating all these variables. So 2n plus 7 minus 2n plus 3, we will get 4. Therefore, degrees of freedom for this flash drum is 4. That's why we can control only 4 variable. If you try to control 5th variable, then there will be a contradiction among the control loops. One loop want to increase temperature, another loop want to decrease the temperature. Like that contradiction may happen. That's why we can control only 4 variables. Then we have seen how to select these 4 variables that we have seen. Definitely, to get quality product, this pressure and temperature inside the flash drum must be maintained. That's why P and T are prime variables from the process aspect, chemical aspect. That's why P and T are controlled. Then to get a constant production, this feed flow rate must be controlled. So 3 variables. And the one more, if the flooding should not happen and the level should not increase beyond safer too much level may also dangerous. Too low level also, the drain out also be dangerous, because of heat is transferred through that heat transfer unit. That's why too little level and too high level both are dangerous. That's why level has to be controlled. That way we selected 4 variables. To control these 4 variables, we have selected another 4 manipulated variables among the 2n plus 7, and we found 24 possible combinations. By qualitative analysis, we selected 4. This is one way. This is qualitative analysis. This can be done quantitative analysis also. That is called that we are going to see today. Quantitative analysis. Quantitative analysis. But anyhow, we have to select the 4 variables, 4 process variables. We have to select the 4 process variables. In this example, 4 process variables. We are talking about that example. That's like 4 process variables and the 4 manipulated variables we selected. But how to which variables has to be controlled by which variable. That can be found by using quantitative analysis that we are going to see today. That quantitative analysis called relative gain array. That quantitative analysis is called relative gain array. Before going to see all these things, we should see more about interaction. Then only we can understand about the relative gain array. Now let us let us see interactions first. Then we will go to relative gain array. Interaction. Interaction means already we have seen that if you increase M1, why we are increasing or decreasing M1 to manipulate Y1. Similarly, yeah, why we have to manipulate M2? It is to manipulate Y2. But it has interaction. That's why if any change in M2 will affect Y1, that can be represented by this H12. This one is for output. The first subscript 1 is for output. The second subscript is for input. H12 means H12 is a transfer function between, if you change M2, a step change is given in M2. Let us assume a step change is given in M2, then observing Y1 by keeping M1 constant. By keeping M1 constant, you will get a response like this. From this, you can model this process. So this is the model between Y1 and M2, that is called H12. Similarly, by keeping M2 constant, if you give any changes in M1, Y2 changes. So you can model for change in M1 for change in Y2. That model is called H21, the dynamics between M1 and Y2. We can call it as dynamics between M1 and Y2. That is a mathematical model for any change in M1. How much it affects Y2 is called the mathematical representation of change in M1 for change in Y2. Here also H21 means 2 represents the suffix 2 represents the output, the suffix 1 represents the input, H21. So now we have in this 2 by 2 process we have 4 transfer function. This is input output transfer function between M1 and Y1, M1 and Y1 keeping M2 constant. This is between Y1 and M1 and Y2, M1 and Y2 keeping M2 constant again. Here this is between M2 and Y1 keeping M1 constant. This is the transfer function for between M2 and Y2 keeping M1 constant. And now we have 4 mathematical models. We have 4 mathematical models to represent interactions. We know about H1 for manipulation of M1. What is the change in Y1? That is already we know. So here we have 4 transfer functions. Suppose you want to control Y1 by using M1. M1 means this is the way by which we have to control. So the feedback is Y1 to Y1 set point, and control is here that manipulates M1. Similarly, Y2 can be controlled by using another controller by manipulating M2. Here Y2 set point, and the feedback is Y2. This way. If we selected M1 to control Y1, M2 to control Y2, then we can write the expression including that interaction. What is Y1? Y1 is earlier how we will write Y1 equal to G1. G1. It is we are not talking GH or same. G1 of S, G1 of S, M1 of S, like that we'll write. But here we have to account interaction also. That's why Y1 equal to what? y1 equal to changes due to m1 as well as changes due to m2. Therefore, we can write y1 equal to h11 m1 plus h12. This one represents output y1. H12 m2 of s. Like that, we can write y2 equal to h21. The transfer function is h2. Manipulated variable is m1. So h21 of s, m1 of s, and h22 of s, m2 of s. That way we can write these two equations. The interaction among the control loops of MIMO process that we have seen, we can find the interaction by using that relative gain array. We can design special control systems without any non-interacting. We will see in the final slides how to design non-interacting loops by using decouplers that we will see. So we are going to see three things. What is the interaction that we have seen? Then what is a relative gain array? Then we'll design how to remove that interactions. That is called a decoupling. How it can be done, that we'll see now. So from this loop, we can write that what is m1. M1 can be written. What is m1? M1 equal to this error multiplied by GC1. What is this error? This error is y1 minus y set point of 1. So error multiplied by GC1. Therefore, we can write m1 equal to GC1, the controller transfer function, multiplied by that error y1 set point, that is set point of s minus y1 of s. So similarly, m2 can be written as controller 2 GC2 multiplied by y set point of 2 minus y2. Now, what is y1? A closed loop transfer function of y1, that is equal to y1 equal to h11. This block diagram consists of h11. You should imagine yourself. Here we have h11. Here we have h21. Here we have h12. Here we have h22. These are mathematically defining the interactions, but as a process, this is the block diagram for the process. It consists of all these things. Imagine like that. So from that we can write y1 equal to h11 GC1 upon this feedback part, the 1 plus h11 GC1 into y set point of 1, because the input is y set point of 1, provided m2 equal to 0. No change in m2. If any changes in m2 happens, that will affect y1. This is true only when m2 equal to 0. Similarly, we can write for second loop h21 by keeping m2 equal to 0. M2 equal to 0. For y2 we can write, if any change is given here, definitely change in m1 will affect y2. That's why change in y2 equal to h21. The forward path transfer function is h21 GC1. This is the forward path transfer function, h21 GC1. But what is the feedback for this controller? Again the same, 1 plus h11 GC1. The denominator is same, but the numerator is changed. So we got y1, y2, keeping m2 equal to 0. In that case, the interaction is there are two types of interaction. One is direct interaction. That is called direct interaction. What we have seen in y2 is called direct interaction because of M1. Another interaction this Y2 is called direct interaction of M1 on Y2. Now let us see the interaction in Y1, indirect effect. Direct effect on Y1 is manipulation of M1. Indirect effect on Y1 is if we change M1, why we are changing M1? Because we notice some deviation in Y1 that is fed back to the controller. Here set point is constant. Here error is noticed because of deviation in y1. That's why this controller takes action. That's why M1 is varying. As M1 is varying, Y1 will be corrected. At the same time, it deviates Y2 also because of H21. Because of H21 in this path, this interaction transfer function, this Y2 is changing. Then Y2 deviates. Here another loop is there. Because of this deviation is why this deviation happened now? Because we are changing M1 to control Y1. That's why Y2 also changing. That's why this Y2 went back because deviation. But Y2 set point is constant. Some error again happens here. That's why now M2 is manipulated to control Y2. At the same time, it deviates Y1 also. This effect is called indirect effect. Change in Y1 because of M1, that is direct effect. Because of H11. Another indirect effect is because of H21, it goes to Y2. Because of feedback, again, it manipulates M2. Manipulation, any change in Y1 manipulates M2 here. You can notice that. So change in M2, what it will do through H12, this is H12 path. This is H12 path. This path is H12 path. H12 again affects Y1. This change in Y1 is called indirect effect. So interaction can be seen two ways. One is direct effect and indirect effect. Similarly, in Y1, direct effect is there. If M2 is changes, directly it affects Y1. That is called direct interaction. If M1 is manipulated, M2 also affected. That is direct whenever M1 is manipulated. Another one is that we have seen now. If Y1 is manipulated, once again I'm telling how the indirect effect comes. Y1 is deviates because of some disturbances entering into the process. That's why Y1 deviates. That's why this feedback path reflects that deviation to the controller. So error generated. Because of that error, this controller takes necessary action to control Y1. That is M1. The output of the controller is manipulated. That M1 affects both Y1 as well as Y2, as we have seen earlier. Direct effect. That Y2 now deviates. Then what will happen? This controller has to take necessary action for this deviation in Y2. That's why this feedback tells the controller that something is deviated when Y2. That's why it compares with Y2, error is generated. That's why M2 is generated to control Y2. That controls Y2 as well as Y1 also it deviates. That is called indirect effect. So again, this deviation in Y2, what will happen? This affects here, and this deviation again, it manipulates this controller. Again, it will get another. This is like throwing a stone in the pond. In a pond, if you throw a stone, what will happen? Continuous waves will come. Like that, this will quench after some time. If any small change happens in Y1, then Y2 will be disturbed. Then Y2 will disturb Y1. Then again Y1 will disturb Y2. Like that, it takes some time to quench. Here, an example for that interaction. And this is the example for interaction. This is CSTR. In that, we have to continuously stir the tank reactor. In that CSTR, we want to control two parameters, two process variables. One is we want to control the level. Another one is we want to control temperature. The steam supplied to this to heat up, it is endothermic process. That's why steam is supplied here. The steam has to be regulated to control the temperature inside. So a temperature sensor is there, temperature transmitter transmits its temperature to the temperature controller, and the valve regulates the steam flow rate. This is temperature controller. Another one is level controller. Level controller, that is H has to be controlled. Level controller. Level transmitter is here that transmits to the level controller. This level controller, if any deviation level is there, it will regulate the outflow rate. It regulates the outflow rate. Outflow rate will be regulated by using this valve. There are two controllers. A set point is given to this controller. Similarly, another set point is given for this controller. This is the two control loops in that CSTR. One for temperature and another one for level. Another one for level. Now, what happens if any deviation in H, some disturbance is coming? Let us assume that the inflow rate Fi changes. Inflow rate Fi changes. What will happen? Slight decrease in slight increase in Fi happens. Then what will happen? Level will increase. This level will increase. Level increase is noticed by this level transmitter, but set point is constant. Set point is given to the level controller. That's why error will be generated. And it generates a controller output M1. M1 controller output will be generated by this controller. That's why this valve will be adjusted. So it will decrease. It will decrease the flow rate. It will increase the outflow rate. It will increase the outflow rate so that level will be adjusted. If we increase the outflow rate, means what is the meaning? There are two meaning. One is mass flow rate increases to adjust the level. At the same time, it takes away some heat also. It takes away some heat also. Because it takes away some heat, the temperature will fall. The temperature inside will fall. The mass in the mathematical model of thermal process, you have noticed that the amount of heat leaving the system is F, outflow rate F naught rho Cp multiplied by temperature at which it is sent out. So this is the amount of heat taken away from the process. If F naught increases, definitely the amount of heat removed from this CS star increases. That's why temperature will fall. What is actually happening? Inflow rate increased. Because of increase in inflow rate, level increases. That's why this level, the level controller noticed that increase in level. That's why it tried to decrease the level by increasing the outflow rate. If the outflow rate increased, the amount of heat taken away along with that outflow rate increases. That's why temperature will fall. Now, temperature, what it will do? Because of decrease in temperature, this will increase the steam flow rate, to maintain the temperature. But any increase in steam flow rate will not affect the loop 1. But any change in loop 1 will affect loop 2. This is called a single direction interaction. The interaction is from loop 1 to loop 2. Interaction is from loop 1 to loop 2, not from loop 2 to loop 1. It is not, there is no interaction from loop 2 to loop 1, but there is interaction between interaction is there from loop 1 to loop 2, but no interaction from loop 2 to loop 1. This is single direction interaction. Another example, it has a double direction interaction. It is double direction interaction. Let us do it. Now let us see about double direction interaction. Double direction interaction. The double direction interaction, let us consider another CSTR. In that, two loops are there. It is exothermic. That's why coolant is there to remove the heat. The loop 2 is temperature controller. For the temperature controller, we have a set point to that. We have a set point constant to that temperature controller. Temperature is measured and it is given to the temperature controller. If any error is there, this valve will be regulated to increase or decrease the coolant. This is the jacket. This is the jacket. The coolant enters into the jacket, will remove the heat inside that CSTR. Another one is concentration control, composition controller. In that composition controller, composition is measured here. If any deviation, set point is given to that composition controller. If any deviation is there, this valve will be regulated. Here, you can notice that double direction interaction. First, let us assume that the loop 1, some composition entering into the loop will deviate. Raw material is entering here. If any deviation in the composition of raw material, definitely there will be a change in composition in the effluent, the outflow rate. So the composition controller noticed, composition sensor noticed the deviation. Accordingly, it generates error and it generates M1 controller output. The value is regulated to adjust the feed flow rate. Why adjusting feed flow rate? If concentration is less, we have to increase the feed flow rate. If concentration is more, we have to decrease the feed flow rate. Accordingly, the feed is adjusted to maintain the composition. The composition has to be adjusted. In that case, if the feed flow rate is adjusted, actually, the feed flow rate is adjusted means what will happen? Definitely, there will be a change in temperature. There will be a change in temperature. Why feed flow rate is manipulated to adjust composition? Because of that, there is a change in mass inside. As feed flow rate increases, temperature will fall. Feed flow rate decreases, temperature will increase. For both, the controller will take necessary action because the temperature is sensed here compared with the set point. If any deviation is there, M2 controller output is generated to regulate this coolant flow rate. This coolant flow rate is regulated. Then what will happen? If any change in temperature, the temperature deviated, that's why it regulates. But because of change in temperature, again the composition changes. Similarly, let us assume that there is no change in composition. This is one-way interaction. If CC, this loop 1 does any change, then temperature changes, that we have noticed. That is one-way interaction. Another way of interaction is there is no change in CC. Composition is not changing, but because of inlet temperature changes or coolant temperature changes, maybe either this or that. Either inlet temperature changes or coolant temperature changes. Because of that, there is a change in temperature inside this CSTR. That's why this takes necessary action to take change this temperature. Then coolant flow rate will increase. Because of this change in T, this CC will affect. The CC will affect. Any change in T, definitely CC will affect. Then it will increase the feed flow rate. Again, the temperature will be modified because of increased flow rate. So in this case, double direction. If CC changes, T changes. If T changes, composition also changes. That is called double direction interaction. This is to understand about interactions. Now let us quantify these interactions. For that, we are using relative gain array. Relative gain array. For a 2 by 2 process, the relative gain array, a matrix consists of 4 elements. 4 elements. They are lambda 1 1, lambda 1 2, lambda 2 1, lambda 2 2 are the four elements. Lambda 1 1. This is the relative gain array for 2 by 2 process. If it is 3 by 3 process, lambda 1 1, lambda 1 2, lambda 1 3, lambda 2 1, lambda 2 2, lambda 2 3, etc. Like that, 3 by 3. Anyhow, it is a square matrix. It is a square matrix. Now, how to find the elements in the relative gain array? First, let us see for 2 by 2 MIMO process. For the 2 by 2 MIMO process, 2 by 2 MIMO process, lambda 1 1 we have to find. Lambda 1 1 means lambda 1 1 means it is a ratio between change in y1 with respect to change in m1, keeping m2 constant. That is numerator of lambda 1 1. What is denominator? Denominator is again change in y1 for change in m1, keeping y2 constant. Keeping y2 constant. This 1 1 corresponds to this ratio. This ratio. It means what? Lambda 1 1 means change in y1 with respect to change in m1. Change in y1 with respect to change in m1. Both numerator and denominator are same, but by keeping m2 constant, here by keeping y2 constant, by keeping y2 constant. So so how to obtain these two quantities, that we have to see. How to obtain lambda y1 by lambda m1, sorry, delta y1 by delta m1, keeping m2 constant, make m2 constant, no change in m2, constant value, steady state m2 value. That time you give small change in m1. Notice the change in y1. What is the change in y1? So the delta y1 you got. For delta m1 for by keeping m2 constant you got. That's all. So numerator you got. How to find a denominator? Here keeping y2 constant. The denominator is keeping y2 constant. In other words, y2 should not be changed for change in m1. Then how we can keep y2 constant? We need a closed loop controller. We need a closed loop controller to keep y2 constant. So to keep y2 constant, we put a feedback loop in second loop, second variable m2 and y2. In that you put a loop. Give small change in m1, observe change in y1. Initially it will change for direct effect, then it comes here. Because of that y2 changes, so that is fed back here. Compared with the set point, error generated, the controller changes this. So m2 now will change. Then this is for change due to m2. Let us assume direct then indirect effect. Then it adjusts this m2 again and again. Because of this change in m2, finally you got one value. That is new y1 because of change in m1, keeping y2 constant. This we have to take y1 value after y2 becomes steady state. Both should come steady state. y1 and y2 both should become steady state. Then what is the change in y1 is this, for change in m1, keeping y2 constant. If you find the ratio between the two, that is lambda 1 1. Lambda 1 1. Now let us see what is the range of value of lambda 1 1. It varies from 0 to 1. Its value varies from 0 to 1. Negative value also may come. If if lambda 1 1 equal to 0, then y1 does not respond to m1. When it will become 0? When it will become 0, lambda delta y1 by delta m1, keeping m2 is constant, you are giving some changes in m1. You noticed changes in y1, no notice 0. It means what? Lambda 1 1 equal to 0 means, lambda 1 1 equal to 0 means y1 does not respond to m1. m1 should not be used to control y1. This indicates that y1 m1 should not be used to control y1. That's all. If lambda 1 1 equal to 1, if lambda 1 1 equal to if lambda 1 1 equal to 1, then it means m2 does not affect y1. m2 does not affect y1. And the control loop between y1 and m1 does not interact with the loop 2 of y2. So here, if you get lambda 1 1 equal to 1, it means m2 does not affect y1. m2 does not affect y1. You notice here, you are getting this you are getting for this, whatever you are getting, for this also you are getting the same value, means lambda 1 1 equal to 1. It means what? What is the difference between the two? The first case m2 is constant. Second case is m2 is allowed to vary, but no change in y1. Same value you are getting. It means what? It means m2 does not affect y1. So that is the meaning. If lambda 1 1 equal to 1, then m2 does not affect y1, and the control loop between y1 and m1 does not interact with loop 2 and m2. In this case, we have completely decoupled loops. So m1 does not affect m2 does not affect m1. m2 does not affect m1, completely decoupled loop. If the value is between 0 and 1, if lambda 1 1 value is 0 and 1, then the interaction exists. Interaction is there. As m2 varies, it affects the steady state value of y1. The smaller the value of lambda 1 1, larger the interaction. And why we are telling like that? You are having one quantity in the numerator, that is because of direct effect of m1, that is divided by something. If the denominator means m2 affects y1 much, means this will be larger value. If denominator is larger, lambda 1 will be lesser. It means interaction is large. It means the interaction is large. If smaller the value of lambda 1 1, smaller the value of lambda 1 1, interaction is more. Interaction is more. If lambda 1 1 is less than 0, negative value, that is also possible. If lambda 1 1 is less than 0, then m2 causes a strong effect on m1, and in the opposite direction from that caused by m1. m1 try to move, for example, in a temperature process, m1 try to increase the temperature, m2 try to decrease the temperature. m2 try to decrease the temperature. For example, this you can notice between the steam flow rate and feed flow rate. If steam flow rate increases, temperature will increase. Let us assume that m1 is steam flow rate, m1 and t. T is y1. If m1 increases, y1 also increases, steam flow rate increases. Feed is another flow rate, m2. If feed flow rate increases, what will happen? Feed flow rate increases, then temperature will decrease. So like that, like that. As temperature increases, in that example you can take, what will happen to composition? Composition decreases, then feed flow rate will decrease, then temperature will increase. So like that, the effect will be in the opposite way if lambda 1 1 is less than 0. In that case, the interaction effect is very dangerous, both are, if lambda values are negative. The same way we can find other elements of relative gain array, lambda 1 2. It means what? 1 represents the output, first subscript represents output, second subscript represents the manipulated. delta y1 by delta m2, keeping m1 constant. Um, uh, uh, Here, what and all involved? Y1, m2, y1, m2. We are finding relation between y1 and m2. What are the other variables involved? Y2 and m1. Other variables involved are y2 and m1. The numerator always we have to keep the manipulated variable constant, therefore m1 constant. In the denominator, we have to always keep this output constant, therefore y2 constant. That's all. So this m1 and m2 you can write like this. So lambda 12 means change in y1 for change in m2, keeping m1 constant, and change in y1 by change in m2 by keeping y2 constant. In the same way, you can write for lambda 21, change in y2 for change in m1, keeping m2 constant, change in y2 for change in m1 by y1 keeping constant. What is lambda 22? Change in y2 for change in m2 keeping m1 constant, change in y2 for change in m2 keeping y1 constant. You can put all these in an array. If you put all these in an array, this this row represents what? Output. First subscript is for output. So this row represents y1. This row represents y2. Second subscript, the column represents manipulated variable. This represents m1, this represents m2. So we put all these together. Then if you add the row, if you add lambda 11 and lambda 12, its value always will be 1. If you add these two in the row wise, you will get always 1. In the same way, if you add this way also, if you vertically, if you add column wise add, then also it will be 1. That is beauty of that relative gain array. So you see here, if you add this way or this way, 1. This way or this way, you will get 1. If you add these two, 0.5, 0.5, 1. 0.5, 0.5, 1. Here, if you add this way, 1. This way, 1. This way, 1. So, if you can add whatever column wise or row wise, each column, each row, the sum will be 1. That is the beauty of relative gain array. Then how to, from this relative array, what we can understand? How to couple the manipulated variable and y1, that we can see here. What is time now? Another 5 minutes. We'll see, we'll discuss how to couple the manipulated variable and here we got a relative gain array that 1001. It means M1 has very strong control over Y1. At the same time, M2 do not have any impact on Y1. Therefore, we have to couple M1 with Y1. Here, M1 does not affect Y2, but y1 has complete control over y2. Therefore, in this case, m1 should be used to control y1, m2 should be used to control y2. Here m1 does not have any control over y1, but m2 has total control over y1. Similarly, here m1 has control over y2, so m2 does not. Therefore, m2 should be used to control y1, m1 should be used to control y2. Here 0.5, 0.5. M1 has the relative gain of 0.5. M2 also have 0.5. Either this can be used or this can be used. Whichever is less cost or whichever is easy to control, that can be used to control Y1. The same way, here also 0.5, 0.5. If you use M1, here you have to use M2. Here you use M2, here you have to use M1. In this case, the interaction is for this 0.5, M1 0.5 less, lesser value. This is 0.75. M2 has direct, the impact is more. That's why the M2 should be used to control Y1 and the M1 should be used to control Y2. For Y1, M2, y2, that we have to use. So this is the final control loop that we are getting, because for the first, and for this it should be in the other way. It should be in the other way. So M2 should be used to control Y1, and M1 should be used to control Y1. So here you remove this and connect here. Here you remove this, connect here. That's all. It's time now. 28. Another 2 minutes. Any doubts? If you have any doubts, you can ask. Any doubts? All are keeping quiet. No doubt. No doubts, sir. Anna Devi, no doubt. Sudarshan, no doubt. Pujita, no doubt. Naveen Kumar, no doubt. Okay. Let us review the relative gain array and finish today's how to find a relative gain array. To find a relative gain array, lambda, we have to find all lambdas. For 2 by 2 relative gain array, it consists of 4 elements. One is lambda 1 1, lambda 1 2, and lambda 2 1, lambda 2 2 are the four elements. What is each element? Lambda 1 1 equal to, in the numerator we have to write delta change in y1 upon change in m1 numerator, for keeping m2 constant divided by change in y1, same change in y1 upon change in m1, same, but keeping y2 constant in the denominator. If you get this, what you have to do, you have to keep y2 in closed loop. To get this, you have to keep y2 open loop. So if you keep y2 second loop open, and if you get the ratio delta y1 by delta m1, you will get numerator. How to get denominator? Put this loop in closed loop and find the same ratio. You will get denominator. The ratio between the two gives lambda 1 1. This way we can get all elements. Now how to find lambda 1 2? How to find lambda 1 2? Lambda 1 2 equal to delta y1, change in y1 with respect to change in m2, keeping m1 constant. Upon this, how we can make this m1 constant means we have to make m1 equal to 0 and give changes in m2 in open loop. There is no loop at all. Change in m2. Notice what is change in y1. That you got the numerator. Denominator also same. Change in y1. For change in m2. Keeping y2 constant. Again, this loop is employed, and you have to find how to give changes in m2. You have to give changes in set point, and you have to get. So this is difficult because to generate change in m2, this is in closed loop. That's why it is very difficult to conduct this experiment. Are you able to notice this difficult? Once again, I'm telling, both are open loop. You can easily get numerator. For denominator, change in y1 with respect to change in m2, keeping y2 constant. Keeping y2 constant. That's why to keep y2 constant, you have to give step change here and you have to notice. But one thing we know that experiments need not be conducted. If you come here in an array, if you add row wise, you will get 1. If you add column wise, you will get 1. Therefore, if you know any two elements, any two diagonal elements, suppose you know this point 7, you know this, you didn't do the experiment. Again, you did the experiment for this, that is 0.6. Then obviously you can write this is sorry, this is this should not be 0.3. You got 0.3. Definitely this must be also 0.7. So this is also a 0.3 you will get like that. Suppose you are getting 0.6, this is 0.4, then you will get 1. Definitely this must be 0.6 and this is also 0.6. So from relative array, we can get the other two elements without conducting that experiment. So no need, only 2 experiments are sufficient to find the other 2 elements. That is also there. Already 34. Let us stop here. Tomorrow we'll see what is decoupler. What is decoupler? We'll see tomorrow. How to decouple the effect of interaction. That we can see tomorrow. Thank you. Thank you, Ananda.